All right. So yeah, first may I introduce myself, but I think we can go over this quickly. Just wanted to mention that I'm basically from the Netherlands, where I did my first studies, but I did my PhD in Germany, and I'm currently based in Vienna because I moved in 2016 to Vienna to work there as 3E Energy Economics and Environment Unit Head. And from 2023, as said, I'm self-employed. So next slide, please. Okay, so what I want to talk about, first, the current status of nuclear development in general. And then dive into the technology a bit more. Give a intro on the basis technology. Then show on with the nuclear development timeline, where is this going? And then dive into the small and medium, or later on called modular reactors. Types, development status, what are the chances, and what are the role in emissions reduction? Next slide, please. So what's the current status of nuclear development? Well, 32 countries have nuclear power plants in operation, and of which 12 in the European Union, in total with 415 reactors. And among these, there are 3 so-called newcomer countries that have nuclear power plants under construction. That is Turkey, Egypt, and Bangladesh. And well, what kind of reactor they're building? The pressurized water reactor is the most common reactor type. It's 3/4 of the operating reactors and almost 90% of the reactors under construction. And applications, well, obvious electricity production, but as secondary energy products, also district heat and process heat, and even hydrogen production is not even only future. Next slide, please. So in a nutshell, nuclear technology, the most common reactor type, the pressurized water reactor. On the picture on the left, you see the schematic nuclear fission process, and uranium fuel rod heats the water till like 325 degrees C. And the water is led to a steam generator and back. And the whole thing is under high pressure. This circuit, 150 bars, so there's no boiling. There's only boiling in the steam generator in the secondary circuit. And there, the water is evaporated and the steam and led to the turbine. The turbine is coupled to an electric generator, and the steam is condensed to water and then led back into the steam generator. And that's the basic technology, well, nuclear technology. And so I will use this later on as a basis to explain other reactor types. Then on the left, about the fuel. Uranium is, this is a so-called fuel cycle. Uranium is chemically extracted from the ore. Then it has to be converted into a uranium fluoride gas for enrichment. That means the increase of the fissionable isotope uranium-235 from 0.7, as it occurs in the nature, to circa 4%. And then the enriched uranium is converted into uranium oxide and fabricated into fuel elements. And after the use, the fuel elements are stored in the water, and after sufficient cooling down, that can be taking several years, they can be stored dry or reprocessed. It's another word of recycling. And finally, the fission products, in case of reprocessing, or the used fuel element as a whole, will be put into a geological storage and kept out of the biosphere. Next slide, please. So now we can look to the timeline of nuclear sector development. And what we see is in the beginning of the nuclear era, so to say, from the 1950s, all nuclear initiatives were purely government-driven. But from about the mid of the 2000s, then private initiatives came emerging. And these private startup companies, they were offering the so-called small modular reactors. The traditional nuclear vendors followed because it appeared to be kind of interesting and attracting investment. And according to the IAEA, International Atomic Energy Agency, in their catalog of last year, 2024, there are 69 SMR concepts, of which 29 from startup companies. And the others are from either traditional nuclear industries or also university or research institutes. All initiatives, there are also initiatives in countries currently without nuclear power, like Denmark, Estonia, Italy, Norway, Poland. There's even a startup in Austria I forgot to mention. Next slide, please. Okay, so what does it mean? Small modular reactor. It used to be called small medium-sized reactor. That's why it was proposed for the title of this presentation. But the meaning changed in 2010, and then the medium was kind of replaced by modular. Generally, both of them, it means a small reactor in a category about or less than 300 megawatts. There are also a few exceptions that go like to 470, but basically it's way smaller than the over 1,000 megawatts of the usual traditional big reactors. Now, what does this modular mean? That means that the required power plant output is not built as one large plant, but from a series of smaller ones instead, the so-called modules. And the production will be in a factory instead of on the power plant site. And this is absolutely necessary for the cost reduction. Usually you have cost reduction through economy of scale, especially with nuclear. But if you don't use it anymore, you have to replace it with something. And that means that you have to produce them in multiples, like a series. That's a compensation. So as an example, the aviation industry, as the picture on the right shows. There's a big hull with multiple airplanes in production. And this modularization, it's also, it's not only in the small modular plants, it's also in the bigger plants where the bigger components are produced as modules, not on the site, but then transported to the site and thereby shortening construction time. And only with the small modular reactors, then the entire reactor is produced as a module and transported to the site. Next one. So what shows is with the small modular reactors, there's a lot of marketing and architecture comes first. You see here 5 examples from nice pictures from small modular reactors, which are mainly showing the building and not what's inside. Of course, if the whole business becomes more serious and you go on their website and they have to apply for licenses, of course they will have to be more detailed in their design description and everything. But this is how they start, and most of them, if they keep alive, and then they actually go through the licensing process with a proper design. So therefore, let's dive into what are they offering. There are 4 main categories of types. The first one, the small water-cooled reactors, they are based on the technology that I just showed before, the pressurized water reactor, or sometimes also the boiling water version in which the water already boils in the pressure vessel. There are other types, they are mainly from the startups. They're the 3 categories: high temperature reactors, liquid metal cooled reactors, and reactors with liquid fuel. I will dive into them with the next few slides. Sometimes the water with the SMR, only the water cooled type are meant, and the others are also called AMR, advanced modular reactors. And I will now briefly explain the other reactor types. So this development of the non-water-cooled reactor types, well, they are not new. They are not inventions of these startups or so. These developments started already in the 1950s and 60s. They're for specific applications. The high-temperature reactors were for the demand of nuclear process heat, besides the electricity. Liquid metal-cooled reactors, they have a much improved fuel efficiency. It's the so-called breeding. And both of them, they have demonstration plants in the past. The molten salt reactor, that is the reactor with the liquid fuel, that was meant to use the other resource, thorium, efficiently. And they have had only experiments, so no demonstration plants. On the bottom, the 3 examples of the operated facilities. Next slide, please. So first one, the high temperature reactor, also called high temperature gas-cooled reactor. So the outstanding feature here is that you have higher temperatures for the better efficiency and for cogeneration. It's from the 300, around 300 degrees, it goes up to 950 degrees. But then you have some design conditions. You need heat-resistant materials, and we can't have water in the core. So the resulting design features are that the coolant is helium gas. Reactor core and fuel are graphite and silicon carbide, all heat-resistant materials. And the fuel is in so-called coated particles. That's on the picture on the right below. You have these very small uranium oxide kernels, and they're coated into 4 layers of graphite and silicon carbide. And there's a resulting additional quality that comes with it for more or less free. It's so-called inherent safety. If the reactors are small enough, which all SMR basically are, then there's no fuel damage possible with any coolant leak or other lack of heat removal. So what any other reactor cannot do, switch off the cooling and then do nothing. You always need some kind of emergency core cooling. This reactor can, then nothing happens. The fuel is that much heat resistant. And you can reach this by a combination of the low power density and the heat resistant materials. Next slide, please. So the liquid metal cooled reactors, and then the metal is then sodium or lead that is heated until it gets liquid. There, the outstanding feature is that you have a really better fuel efficiency and therefore lower waste production. And that's especially because of the better use of uranium-238. And the idea is if you have a regular PWR, the picture on the top right, it shows the composition of the spent fuel. So 95% is still unused. It's still uranium-238, and yeah, only a very small fraction has actually been fissioned, and the rest, yeah, sometimes it is reprocessed, but most of the time it's just declared a waste, which is waste. And so what is then the additional qualities? That you have a low pressure, you don't have a big pressure vessel, and it can also burn the spent fuel from other reactors. But it comes also with some challenges. With sodium, you have a high chemical reactivity with air and water, and with lead, you have a high density, so it's just a heavy thing, and you have a high melting point. You have to keep it liquid everywhere in the circuit. With close to the fuel, it's easy, but in all the tubing of the steam generator and everything, it's difficult. Next slide, please. So the reactors with liquid fuel, they have as outstanding feature also the better fuel efficiency and the lower waste production, and also are very suitable to the use of thorium. And the idea is here you have the fissile material in a liquid form. It is dissolved in molten salt, and it's different types of salts. You can have fluoride salt or chloride salt, and the fission products are filtered out during the operation, and new fuel is added, and therefore it's very fuel efficient. The additional qualities are also the low pressure and that it can burn the spent fuel from other reactors. But the challenges are, yeah, the corrosion. As salt, as you know, if you've ever been at the beach, it's very corrosive. And there's what we call in the nuclear field a missing safety barrier because the fuel is not into a kind of casing. There's also related concepts that have still solid fuel elements, but only molten salt cooling. And you have also a version with dissolved fuel that is in cassettes that will be then exchanged as a cassette. Next slide, please. So which SMRs are then actually operating and under construction? Well, there are only 2 plants in operation at the moment. It's a PWR-based plant in Russia. It's a floating plant. They're very kind of special. The name is Academic Lomonosov, and it's in the Siberian city of Pevek, where it is delivering heat and power. So here you see on the picture, that it's basically a barge which is powered by tugboats. Well, powered. I mean, it's moved by tugboats. The other one operating is a high temperature reactor, HDRPM, in Xiaoduan in China, and that's on the picture on the left bottom, right bottom. There are 4 reactors under construction at the moment of this type. What I mean, SMR deliberately built small size. There are still several other smaller reactors, but they're kind of old. And yeah, in the early 60s, from conservative reasons, and it was not immediately over 1,000 megawatts that were built. But this one, SMRs built as deliberately small size, under construction in both, well, 2 in the United States, both, yeah, 2 in the United States, one HTGR Hermes, it's called, by a company named Kairos Power, and a molten salt reactor, MSR1, called by a company Natura Resources. In China, there's also a PWR-based reactor under construction, and in Russia, another PWR-based reactor. That's basically based on the floating plant technology, but this time it's under land-based. Yeah, next slide, please. So, what are the chances for SMR? Well, compared to the early days of nuclear power and also the more recent decades, there are some recent changes. The SMR concepts are mostly not new, but there are now these private initiatives that are getting a lot of funding, basically. Energy systems currently have large proportions of intermittent renewable energy. There's a demand for stabilization. The climate problem is taken more seriously. There's increased awareness for the need of energy security of supply, and also increased political support. Also, there's an increased demand of additional sectors, like the data centers that just used not to be there. Mining in remote locations also found nuclear power as a possible power source in their mining activity. And back from long time ago, the maritime applications have increased interest at the moment. And there are several innovations like energy storage in molten salt, so you don't need to move the reactor up and down. There's 3D printing and new welding techniques application to shorten construction times. You already put the next slide, thank you. Moving to climate change mitigation. So the figure at the left is from the International Energy Agency. There it shows that the energy sector is responsible for about 45% of greenhouse gas emissions. It's basically all the blue sectors and the light green one. And according to the IPCC, that is the right picture, nuclear energy is among the low carbon technologies. I must remark here that this is only for the kilowatt hour as it's produced. It's not, you should basically, for the intermittent sources, compensate for the battery technology that also has to be produced to together have a dispatchable energy source. Next one. So about the political recognition, it has been growing recently. There's these 3 events. The first, the European Union, they came with their European Net Zero Industry Act in 2023. Their advanced nuclear technologies are categorized as net zero technologies. The financial sector followed suit. They supported a pledge from 14 of the world's biggest financial institutions in last year. And then there are the climate change conferences, the famous COP conferences, 28 and 29. There was a group of 25 plus 6 countries. They pledged support for tripling the nuclear energy capacity by 2050. So nuclear energy, can be said, is here to stay. We have here on the right the director of the IAE, of the International Energy Agency. We do not have the luxury to exclude any clean energy technologies if we are serious about addressing climate change. Now, what can ASMR then do? They can support these emission, supplement these emission reduction efforts, complementing the traditional large reactors. So the traditional large reactors will not be replaced or so, but they're just added. There is less cooling water needs, and therefore there are more potential locations. And the location will be closer to the energy user, so the potential for heat and hydrogen as energy products is increasing. So with this, I thank you for your attention. That's the last slide. Here you can see my email address, my affiliations again. Bèta Research is just my company, as I made myself as self-employed, and I'm an independent consultant within the partnership of Nuclear 21.
Yeah, Aliki, thank you very much for this excellent presentation.